Good afternoon. I'm David Wilco, and I have the distinct pleasure of introducing our speaker today, Paul Elsen. Paul is a conservation scientist, in particular a climate adaptation scientist at the Wildlife Conservation Society. And Paul's ties to Princeton go back a number of years. He was a doctoral student here in the Department of Ecology and Evolutionary Biology, and I had the great pleasure of being his advisor. He received his PhD in 2015 for a dissertation that looked at interacting roles of climate, habitat choice, competition between species, and land use change affecting the distribution and the conservation of Himalayan birds. And it was an extraordinary dissertation, both conceptually and in execution. I think, Paul, we once tallied that you had spent about 2 years in total, mostly camping and backpacking in the Himalayas to get the data for your thesis. And it led to some really terrific things. After his time at Princeton, Paul received a David Smith postdoctoral fellowship to go to Berkeley, and that was followed as well by a postdoc at the University of Wisconsin, where he worked with Volker Radloff. And after that position, he joined the staff of the Wildlife Conservation Society. Now, during the time after Princeton, Paul's interest in conservation science never waned, but he continued to expand the range of topics that he worked on. So he did some really terrific work to determine how well the network of today's protected areas protect elevational gradients, because you can imagine in an era of climate change, species will need to move around, and in particular, the montane species, many of them will want to move upslope. He has done work on the climatological factors that drive the distribution of birds, which is clearly relevant in this climate change era, as well as studies on how patterns of deforestation around the world have shifted over time and what this bodes for both the conservation of biodiversity and the sequestration of carbon. At the Wildlife Conservation Society, Paul has worked very closely with scientists and conservationists in Afghanistan to help them build the tools they need, the analytical tools they need, to develop and manage the network of protected areas in that country. Sadly, this work has had to be paused in the wake of the Taliban takeover. But Paul continues to reach out and work with people in other countries, again, helping to bring to them the skills that will enable them to deal with new challenges in designing protected areas. And I have to say, in my mind, Paul is one of those very rare scientists who seems to be able to do just about everything. That includes rigorous field work, big data analysis, modeling, and he does it with what I think is a very keen sense of what questions really need to be answered in order to advance conservation on the ground. And with that, it is a real pleasure to welcome Paul Elsen back to Princeton. Paul?
Thanks so much, David. Thank you, everyone, for coming. It's really an honor to be here. I've spent many times having sandwiches in this room and enjoying amazing talks. So I'm really looking forward to discussing this work on some more recent work of mine, identifying ecologically viable climate refugia under rapid global change, and I'll kind of get to that in a second. First, I do want to back up a little bit and acknowledge the support and guidance of David, who just introduced me for all the support that he's given me over the years, both at Princeton and beyond. As he mentioned, he's my PhD supervisor and really shaped my time at Princeton and my career so far in tremendous ways by influencing me to study the distributions of Himalayan birds and understand the climatic factors that underpin their distributions, how they're threatened by both climate and land use change, what we can do about that. And here's a picture of us at one of my field sites in India in 2013, which was really a highlight of my time at Princeton. He's also celebrated a lot of big moments in my life with me, including attending my wedding later that same year, and eventually celebrating the successful defense of my dissertation, which of course is what I was working towards the whole time. And over the course of these 5 years I spent with David, I always valued his honesty and his sage wisdom. I think he had a knack for understanding the successes and how to achieve really great things. And so I was a little perturbed and dismayed, I guess, when he, at the conclusion of this evening, took me aside and said, "Paul, the life of the mind is not for everyone." And that stuck with me. It really, was a low point, but everyone needs a push, and despite my resentment and my better judgment, I've continued to be close friends and collaborators with David even to this day, and here's some proof of that in a recent trip. Many of you probably also know that David's career in conservation, such as it is, started in the nonprofit sector, working for a couple different environmental NGOs. First the Wilderness Society, and then later the Environmental Defense Fund. And I think he was drawn to that to really do good conservation work on the ground and not just the science that sort of in the academic setting. And I really, that also really resonated with me, and I had similar aspirations to kind of do really good science, but also make sure that they had an application on the ground. So I was fortunate enough to join the Wildlife Conservation Society about 3.5 years ago, and supporting in WCS, they work, it's a nonprofit organization that's mission is to save wildlife in wild places. They work in 14 global priority regions across the world in about 65 countries. And I was really inspired by the opportunity to work in a science-driven organization that had the relevant and necessary governmental, political, institutional connections on the ground in many of these places to actually get real work done. And so when I joined Wildlife Conservation Society as a climate adaptation scientist, I started working with the Afghanistan program, but I transitioned into working on a number of really exciting projects all over the place, supporting our field programs, our country programs, in developing science around climate change, vulnerability assessments in Rwanda, in Afghanistan, doing some climate smart conservation planning in the US and Mexico, and then doing a lot of capacity building and training around climate adaptation and geospatial science in South America and in Myanmar and other locations. And it's been a really positive experience so far. But today I want to talk about another aspect of my work that I've been doing at WCS that is trying to support a global initiative to support the conservation of biodiversity, mitigate climate change, and influence the resilience of both ecosystems and communities to climate change through adaptation. And that's why I want to talk about identifying ecologically viable climate refugia under rapid global change today. So I'm going to walk through a quick introduction and background, which will be sort of familiar to most of you, and then talk about the Holdridge life zone model of ecosystem classification, which some of you may have heard of, and then talk about the work that I've been doing to map life zones both historically and currently and into the future to see how life zones, which are particular places of different kinds of climates suitable for different types of ecosystems and biotic assemblages, how those are likely to change over time, which has some impact on risk and vulnerability. and then look at identifying viable climate refugia, and I'll define that later on, and before getting to some policy implications of this work. So climate change, as we all know in this room, is impacting biodiversity worldwide, and I really like this figure from a recent review paper because it shows that not only is biodiversity impacting all these different organism groups in all of these different places worldwide, but it then links changes in species distributions to consequences for governance, for ecosystems, for people and cultural societies as represented by those colored pie charts. These are only illustrative, they're not exhaustive, but it's a lot to take in, and you can see just the breadth of impacts that climate change is having on biodiversity. It's also impacting ecosystem function, and another review paper from right around that same time did a really great job of enumerating all of the ways in which climate change is impacting ecosystem function at various scales, from genetics and physiology to morphology, phenology, species dynamics and distributions and interactions, at all these different levels of organization. And most of the time, this is concerning because it has destabilizing effects on ecosystems and impairments to resource distributions for people. So climate change is obviously impacting human well-being, not only directly, but through the changes in ecosystems and biodiversity patterns. At the organism, population, species, and community scales, we see multiple different effects of climate change on in terms of increasing herbivory on crops and resources that will reduce economic value for people, changing species distributions, which might change the distribution of pollination services or pathogens that affect different resources. And again, that all then affects people as well. And the links between climate change impacts on biodiversity, ecosystems, and people are just becoming stronger and more well understood as we do more research. An overall vulnerability of people, of ecosystems, of biodiversity is usually a result of the level of exposure to climate change that organism or system is experiencing, their sensitivity to that change, and their ability to cope with that change or their adaptive capacity. So the concept of climate stability in this context is really, really important because areas with more stable climates, by definition, sort of have lower exposure and often have higher adaptive capacity to minimize the risks associated with climate change. This chart is probably familiar to most of you. It's taken from the IPCC's 6th assessment report. On the left, it's just showing climate projections for global temperature change out to 2100 based on a reference period of 1850 to 1900. Each of the colored lines is a different sort of climate scenario. And you can see temperature changes on the y-axis. You can see the divergence in those. But on the right, it's linking the different levels of exposure of just temperature to different aspects of risk for ecosystems and people, where you see the purple is very high risk, the red is high risk, and so on and so forth down to moderate risk. And you can see that with increasing exposure across a range of different types of systems and impacts, we see risk increases. This is true even if you look across a wide variety of terrestrial and freshwater ecosystems. On the left here, it's the same structure as the previous plots. You can see it's impacting biodiversity loss, structural change, tree mortality, etc. And then on the right, it's showing the same thing for risks to oceanic systems. And you can see here that across the board, areas with lower exposure, higher climate stability, are associated with lower risk. And so that's an important principle that has driven a lot of people to want to study and understand climate stability over time and over space. As I mentioned, climate stability is not the only factor that influences vulnerability. You also have the potential to actually do things to the landscape or to a system to decrease its risk by investing more in adaptation actions. And you can see here, we're looking at climate impacts now on human health outcomes, from heat-related morbidity and mortality to ozone-related mortality, malaria, and dengue. And different ranges of how much adaptation or investment there is. And you can see that with increasing adaptation, you lower the risks. You're investing more in building up the resilience of those systems. But if you have low climate stability, you don't have to invest as much across the board here again. You can get away with limited amounts of investments and still have positive outcomes if you're able to understand and work in these climate stable areas. So this recognition of the importance of climate stability has led a lot of scientists to try and understand the spatial distribution of climate stability over space and over time, using a wide range of metrics that differ in their assumptions, that differ in their results. Here I'm just showing kind of 4 common ones. The velocity of climate change in the top left is probably the most familiar to a lot of us. It's the rate at which a species must move its distribution to keep pace with climate change. The bottom left is something called thermal niche shifts, which just acknowledges that organisms, and I think this is for humans, organisms have sort of a thermal environment that they're comfortable living in, and as the temperature changes over time, that space occupied by that thermal gradient will change to make some areas more unsuitable, which would be shown here in the red. And then 2 different metrics of climate stability, which are multivariate metrics that look at basically how different along several different indicators of climate, mean temperatures, precipitation, seasonality, and all those effects, how different is the climate in the future going to be from the present at any given locality. So the higher the dissimilarity is, the lower the stability is. These metrics have been very, very influential in driving conservation and understanding of risks for both biodiversity and for people, but oftentimes they're just they're limited in only understanding how the nature of climate, the magnitude and the trajectory of that climate is going to change. It doesn't actually link to potential ecosystem distributions and actual biotic assemblages that would shift as a response to the changes in climate, which is what we kind of can care about and can manage a bit more in a practical context. So my work has been focusing on this alternative system of ecosystem classification called the Holdridge Life Zone System, which was actually introduced in 1947 by Leslie Holdridge, who was a botanist and published this paper in Science where he called them world plant formations, and later developed the concept much more in the 1960s, put out a really big book on the subject where he called them life zones. And he recognized that life zones and described them as natural sets of associations that comprise equally weighted divisions of the 3 major climatic factors, namely heat, precipitation, and moisture. And he created this chart, which is very faded in his original manuscript that's practically illegible here, I'm noticing. But the right sort of axis on this side is sort of what he determined as biotemperature, which is a mean temperature used to approximate those of the growing season. And the bottom axis is precipitation, which is just sort of the average annual amount of precipitation that a certain locality receives. And using these 2 factors alone, and looking along a logarithmic scaling of these factors, he discovered that temperature and precipitation values for any site plotted logarithmically on this chart determine a point which falls within a hexagon representing a formation. Originally, this was a plant formation, like a plant ecosystem type, but later was described more broadly, recognizing that it's also relevant to wildlife and animal communities as well. So for example, an area, a station with a mean of 8 degrees Celsius and a 360 millimeter rainfall would fall in the cool temperate steppe, which is highlighted there in that green hexagon. The left-hand axis here, there's a third axis, which is a sort of an aridity index, and the evaporation lines were hypothesized by Holdridge to represent the amount of time, number of times in a year that actual precipitation could be evaporated in any given year, but he lacked any kind of data or real concept about whether or not these were actually informing these life zones. these were never tested by him, and we actually did, now that we have the data, start to look into some of his assumptions. But that's not really the topic of my discussion today, so I'm not really going to touch on that. But it's really interesting that what we found in that regard was that he was mostly right. Most of his assumptions and predictions were what we found in reality with some minor deviations. This is a modern update of the life zone model. You can see that there are about 40-odd life zones in this model, and you can see the three axes, the annual precipitation, biotemperatures all the way there on the right-hand side, and then this aridity or the potential evapotranspiration to precipitation ratio, and then showing where you fall into describing sort of boreal moist forests, distinguish between cool temperate moist forests or wet forests, and then as you move further down, you get into the warmer and wetter parts of the grid, where you're getting to tropical, rainforests and things of that nature. There are several advantages of the life zone model that makes it really suitable for not just an ecosystem classification model, which is a sort of simplistic approach, but also for linking climatic parameters to ecosystem distributions and allowing us to actually model these over time. And there's advantages over a lot of competing models that do similar things. One of the major features of it is that the life zone model is dynamic and defined directly from quantitative data. It doesn't rely on subject opinion like terrestrial ecoregions, which are very valuable in their own right, but which ultimately are delineated on a map as a static unit representing a particular place that's always been that way, is always going to be that way, and is devoid of any kind of climatic parameterization. And it also differs from things like remote sensing products. Over here on the right, the Dynamic World dataset came out earlier this year, which gives us near real-time classifications at 10-meter resolution globally using decades of satellite imagery and remote sensing and hundreds of thousands of training points to create a super sophisticated product that's updated all the time, but you can't really forecast with that information. It's not climatically linked, and it only can give us kind of a good view of historical transitions. That's not the case with the life zone model. A second advantage is that the life zones are based on continuous rather than categorical measures that have been validated. So there's other competing climate classifications out there, like the Köppen-Geiger, which use sort of somewhat arbitrary thresholds to define these climatic zones that are actually not representative of ecosystem types in terms of plant formations and wildlife formations. So it's a little bit less applicable to the conservation and management of natural resources. Third, the climatic variables that are defining life zones were chosen because they directly constrain ecological and ecophysiological processes. And there was a paper earlier last year, actually, that used the life zone principles to map out how food crop production and livestock production were constrained within the life zone space. You can see on these two diagrams. And if you can see the sort of light blue polygon shows what they mapped out as the safe climatic space, the space that we actually see food crop being produced within and livestock being produced in from a physiological standpoint, and then projecting using the life zone model where that space would occur in the future within those red dots. And you can see sort of a shift and a contraction of those because those processes are constrained by the climate. And lastly, the life zone model has been characterized and compared against a lot of other competing models, and it shows generally a high correspondence to them. So things like the Bailey ecoregions, potential vegetation classes, biome distribution models all have a very similar general appearance as the Holdridge life zones, which is the top left there. It deviates slightly from sort of land cover classifications because the life zones system only looks at natural potential vegetation types, not human land uses. There have been several different applications of this worldwide. I mean, hundreds, in fact. I'm just showing 5 examples of different applications of the life zone system in different countries, from Turkey, China, Argentina, the US, and Costa Rica. And these applications have served not only to sort of map out and understand the distributions of these places at finer scales, but also to actually validate the models by using field measurements and understanding whether or not this system has any resemblance to reality. And overall, it does seem to do fairly well, with some limitations in more seasonal environments, which has no component in this system. But it's especially developed and applicable for tropical forests. There have been several attempts to map life zones globally. The earliest example I could find was in 1985, using some pretty coarse half-a-degree resolution information, which was repeated again in 1992. And then in 2011, I found a very coarse analysis, but it was the first one that I could find that actually looked at forecasting life zones into the future to understand life zone distribution changes. You can see it's massively limited in its applicability or usefulness, given its 155 square kilometer resolution. And then, like as I mentioned last year, there was a study that came out that mapped these and projected them at a much higher resolution. Our goal was to improve upon these models and hindcast and forecast them to understand climate stability from a life zone perspective at resolutions that were applicable for management, so at a 1 kilometer square resolution. So as a reminder, the components that are required for this are the biotemperature and annual precipitation. And we used a global data set of climatologies called the climatologies at high resolution for the Earth's land surface areas, called the acronym is CHELSA, which is a high resolution data set of freely available climate data sets for terrestrial land areas, including monthly mean temperature and precipitation patterns for various time periods. It's similar to things like WorldClim, if you're familiar with other gridded products, but it has a much more sophisticated downscaling algorithm that makes it much more accurate for precipitation projections, which, because they're so influential in life zone characterizations, it's really important to get those right. So it's a big improvement on other competing models. We used this 3 different flavors of CHELSA to delineate 3 different time periods. We looked back using the CHELSA-CRUTS data set to look at historical climatologies from the early 1900s. We used their contemporary climatologies data set from 1979 to 2013 to bound a contemporary period. And then we used projected climate information that was downscaled from CMIP5 climatologies for 2 different time periods, around 2050 and around 2070. And for those future projections, we looked at a range of different climate models. We looked at 5 different global climate models that we chose to maximize their independence from one another. And for each of those, we looked at 2 different emission scenarios, sort of a moderate emission scenario, RCP 4.5, which is a couple degrees of change, of increase in temperature, more or less, and then an RCP 8.5, which is sort of the business as usual or high emission scenario, which is a much higher rate of temperature change. And we used each of these emission scenarios for all the 5 climate models for both of those 2 time periods. So the biotemperature is defined as the mean annual temperature change clamped to the range of 0.75 degrees to 30 degrees to bound this life zone space. So when we take the climate products from CHELSA, we were able to map out historical biotemperature, showing the 6 different climate bins in life zone space, the contemporary biotemperature, and then the future biotemperature. And if I kind of toggle between these a little bit, you can see there's a much smaller change between the historical and contemporary periods as there are between the contemporary and future periods, despite the fact that it's an equal amount of time that's changed. And that's because the rate of climate change is increasing, as we all know. The second component is annual precipitation, and that's just the total annual precipitation at a given site, clamped to the range of 62.5 to 16,000 millimeters of rainfall. And again, we mapped out the 8 different climate bins of precipitation historically, in the contemporary period, and in the future. And it's tougher to see the changes of these. It's not so stark and dramatic across time, but you can see that there is change happening between these different periods. And these future projections, I should have mentioned, are ensemble averages across each of the 5 global climate models to take account of that variability. Sorry, the units in the temperature are degrees Celsius, and the units in the precipitation are millimeters. I'm sorry? Darker, this doesn't relate to climate stability just yet. It's just the amount. These are just the components that go into the life zone. Thanks for the question. So combining the precipitation aspect component and the biotemperature aspect gives us the life zones. And you can see we've updated the life zone table even further. It's no longer sort of a pyramid because we actually discovered that there are portions of life zone space out into the colder and drier portions that were predicted by Holdridge. So this is the historical picture of the life zones, the contemporary picture of the life zones, and the future prediction of the life zones. And you can see again the changes where you're seeing an expansion of certain life zones into the future, contraction of others over time and over space. When we look at the changes in life zones over space in the historical period to the contemporary period, we see that 27 million square kilometers of land has shifted already between one life zone to another, and those are shown in the colors in the map on the right. And you can see the sort of a pie chart there showing the different colors. Those colors represent to either wetter or warmer or drier life zones. Any of the black areas are what we classify as stable, meaning they were in a particular life zone in the early 1900s and they've persisted as that same life zone over time. This plot on the left is showing you those transitions where you're starting in the historical period. Each one of these little bands you can kind of just pick out is the area of an individual life zone and then showing the amount of area that it is in the future. And these bigger windows are sort of all of the life zones that are in the sort of bottom end of that table. And you can see that the difference in the heights of those show larger expansions or contractions of these different life zones. When we transition to going from contemporary to future periods, you can see that the number now jumps to 62 million square kilometers of land is projected to change to a new life zone. We see much more dramatic and contradictory shifts in these different distributions. And on the right plots, the middle one is the areas that are transitioning to a new life zone under the moderate emissions scenario, and the bottom map is the new transitions under the high emissions scenario. So you can see the spatial distributions of those changes, and the colors represent sort of the broad nature of those changes as well. We did not do an exhaustive attempt to validate our models at this large scale, but we were interested in trying to find some examples to see if our life zone projections of what happened between the historical period and contemporary period reflected what happened in reality on the ground in places that were more devoid of human activity. So here's an example from Senegal. The picture on the left is from the mid-90s. The picture on the right is in the early 2000s. And you can see that the desertification of this furlough region has led to a stark transition in the ecosystem type, described very thoroughly in this paper. And we looked at, in our projections, we found that even though the time period doesn't match up quite right, we found good evidence of this happening by looking in the historical time period. The whole region was what was described as tropical thorn woodland. And in the contemporary period, we saw this encroachment of desert thorn scrub coming from the north. And that's reflecting of what happened on the landscape. And another cool example that I really like was going back even further to look at Alexander von Humboldt's pioneering work in Chimborazo in Ecuador, where he did these amazing surveys along the volcano, surveying the plant communities to map out vegetation belts. He was an amazing person. He created this painting called a tableau that he painted back in the early 1800s of depicting those different elevational bands and what their sort of vegetation types were. And then about a decade ago, people went back and redid it, and they updated this tableau, and they found this upslope shift in vegetation that they determined was both climatically driven and driven by human activities. And we looked at this volcano, and you can see that our models capture some of these dynamics, where we see a contraction of the polar area in the center, a contraction of the subpolar rain tundra, that little patch sort of on the right-hand side, an expansion of the boreal wet forest, an expansion of the cool, temperate, moist forest that kind of mirrors what was observed over this time period. So that gives us some confidence in our models. These life zone changes have huge consequences for ecosystems, consequences for biodiversity, and consequences for people, which I've already discussed a little bit. But here is our sort of attempt to just look at what this looks like. Again, I recognize that biomes and ecoregions are kind of the common way that we represent static representations of ecosystem types. And we can see here that on the left-hand side is the comparisons between historical and contemporary distributions for biomes and then into the future. And on the right is for ecoregions. The darker colors are how much of those ecoregions or biomes is going to change to a new life zone. And this just emphasizes that, a huge percentage of certain ecoregions, over 80%, will transition to a new life zone. So this cannot be used as a static system for sort of ecosystem or conservation management, because they're not static and they're being treated as such. In any case, the systems that were affected the most are boreal forests, montane grasslands and shrublands, temperate coniferous forests, and deserts and xeric shrublands. We looked at how life zone changes are impacting threatened species and areas of high endemism. And we saw here plotting out life zone area changes on both of these, and then the mean number of threatened species. We don't see a very stark relationship with the number of threatened species or with levels of endemism. And that's basically kind of bad news, actually, because what we're finding is that life zone changes are occurring everywhere. It's not just that the areas in the polar regions that don't have as many species, maybe lower conservation concern, are the ones being impacted. It's across the board. We're seeing tropical areas transitioning, temperate areas transitioning, and areas of high conservation value. And that's really, really important. There are numerous examples that I can go over about the consequences of these changes for humans and livelihoods and people. I've put a lot up here mostly related to shifts in agricultural suitability, but also things like changes in stream flow dynamics. And the example on the far right is kind of interesting, where they mapped out how climate change will change the distribution of different kinds of timber plantations and tree species of different economic values. And the bottom shows that with this transition to different kinds of timber species, the economic return will be about 30% lower than it is currently by the end of the century, which has obviously big impacts on people's income and those kinds of things. There are obvious limitations to this approach. It is a very simple system, and I think the most important one was recognized by Holdridge himself when he described that local edaphic conditions such as salinity or high water table, as well as alteration by man, obviously change the appearance of vegetation to a great extent. These life zones represent potential vegetation, not actual vegetation that's on the ground. So they are sort of a system that is saying, if you don't have people around, if there's no other competing opportunities or resources there, this is what would likely support these types of ecosystems. We know from a lot of work that that's just not what's happening in reality. That the top map shows the global anthromes, or areas that are human-dominated systems, and you can see sort of the rise in human-dominated systems over the last 8,000 years. So we know that humans are having a huge impact on the land area, and that we need to understand that life zones are potential and not what's happening on the actual ground. They're also not accounting for any kind of physiological or geophysical limits, so they're not going to be able to be descriptive of vegetation structure or function. They're also an equilibrium model, which means that they assume that with climate change, the vegetation is going to change instantaneously, which is a huge oversimplification of reality. And that's just something that we have to acknowledge the limitations of this. Nevertheless, the system provides a very promising and powerful tool to map out stability, going back to the sort of start of this talk, where the areas in blue here are the areas that are projected to become remain stable in the same life zone, and the areas sort of in the gray are those unstable areas. And this has a lot of value for conservation, but we know that these areas cannot function fully if they've been heavily impacted by people. So our latest work has attempted to then integrate metrics of human pressure into this model to understand where life zones are stable and have minimal human pressure to actually make them viable in terms of their refugia potential. So for that, we use a metric called the human footprint, which is a composite metric of 8 different pressures on a scale of 0 to 50, 50 being the maximum impact from all the pressures, 0 being no impact from any of the pressures. The 8 pressures being things related to croplands, pasture, population density, nighttime lights, and different kinds of transportation. And we can use this data set to then understand a bit more about what kind of impact humans are having on the landscape. Oftentimes, that scale from 0 to 50 gets converted using a threshold to identify and distinguish intact lands from modified lands. This is a simplification again. There's a lot of sensitivity you can do to test these thresholds, but in general, they have been validated so that a threshold of 4 represents something about a cropland, and anything higher than a 4 is a cropland or more intense that is likely to increase extinction risk. And under a 4 is sort of not built up to that point, is relatively intact, and has reduced extinction risk. So applying that thresholding, you can see the mapped distributions of intact and modified lands. The combination of this life zone stability map and the ecosystem sort of intactness map allows us to actually identify these ecologically viable climate refugia, which are those climatically stable regions in a life zone context with minimal human pressure, which allows species to potentially adapt in situ and act as source populations to nearby areas. So the combination of those two maps from the previous slide give us this map that shows 4 different categories along the axes of life zone stability and the human footprint, stable intact being those ecologically viable conservation climate refugia, and then areas that are in the light blue are those that have been modified but actually will have stable life zones. If they weren't modified, they would be acting as the same kind of refugia. And the pink values show areas that are not climatically stable from a life zone perspective, but are either intact in the dark scenario or modified in the light pink scenario. Overall, we found that 19% of Earth's terrestrial surface falls into this bucket here as being stable intact. And that's a huge issue because we know that the terrestrial surface has about 45 to 50% of it being, 55% of it is stable, but only 20% of that stable area, or 20% of the total area is both stable and intact. So there's a huge amount of land that is stable but is not functioning in the way that we would want it to in terms of providing refugia. We looked at the distribution of these different categories across the biomes, and we found out that most of the stable intact land is in deserts and shrublands, tropical and subtropical grasslands and savannas, in tropical, subtropical, moist broadleaf forests, and then to a lesser degree in the taiga, boreal forests, and then temperate forests. Less than 50% of Earth's remaining intact landscapes are actually stable, and that's really important because protecting the last of the wild has long been a major priority for conservation, but we know that less than half of those areas that we've been prioritizing are likely to be projected to shift into something completely different over time. And that's going to actually impact the ecosystems, the species that we're actually trying to protect in those areas, not to mention the resources that those areas provide to local communities. We then went a little bit deeper to look at the distribution of these 4 categories with respect to key conservation areas, including indigenous lands, protected areas, and key biodiversity areas on the left here, and then 3 different groups of terrestrial vertebrates that are threatened. In terms of the conservation priorities, we found that stable intact lands only have 22% of them are protected. So there's a huge estate that's still unprotected, that's stable intact and should become premier priorities in the conservation agenda. 42% of stable intact lands are on indigenous lands. So there is a huge role for local communities and indigenous communities to become, to secure these lands for conservation. And so conservationists will need to work with those communities to establish ways to effectively manage them for that purpose. In terms of the threatened vertebrates, we found that about 50% of all these groups combined, ranging from 40% of amphibians to about 70% of mammals, have their distributions in stable intact lands. So they have a huge, stable intact lands have a huge responsibility, I guess, for protecting endangered and threatened species. This is a plot showing the distribution of these 4 different types for all the countries globally. You can't read the countries, I recognize, but the main point of this chart is just to show how many countries have climate stable, intact, stable landscapes and how many do not at all. And that's really going to help inform where conservation actions and priorities should be placed in different contexts. Where we find large areas of intact, stable lands, we might be advising more concrete protection of those landscapes. But where we find large areas of stable modified, we might find opportunities for restoration that will serve, will be more resilient to climate change overall. I want to just turn now to some policy implications of this, and the most obvious point to start is with the Convention on Biological Diversity, which is right now in the midst of finalizing their post-2020 global biodiversity framework to set us up for the next 10 years of conservation targets. And the first target is to ensure that all land and sea areas globally are under integrated biodiversity inclusive spatial planning that retains intact and wilderness areas. And the recommendation based on this work for these is to include life zone stability or any kind of climate stability metric in conservation planning to explicitly address climate risks in those prioritizations. There have been a couple really big papers that have come out this year and last year doing amazing work at really high resolution, plotting out the priorities for conservation, priorities for biodiversity, for carbon storage, and for ecosystem service provisioning to people. And those are huge steps in the right direction, but they omit a key variable, which is some kind of stability metric that can actually completely change how you manage or attempt to protect those areas that they're prioritizing, and could miss very, very important landscapes which are going to change something else entirely. So just by including an extra factor related to stability can help inform more resilient priorities for conservation. Target 2 is to ensure that at least 20% of degraded freshwater, marine, and terrestrial ecosystems are under restoration, ensuring connectivity among them and focusing on priority ecosystems. Recommendation 2 then is to target stable modified land for restoration to boost adaptation potential to restore ecosystems to kind of what they used to be, because they're likely to maintain that stability over time and be able to maintain that type of ecosystem. At the same time, an alternate recommendation for this is to understand what life zone you're transitioning to in those unstable modified landscapes to anticipate what could thrive in those areas into the future. And these maps that we're showing here help guide those priorities as well. And the third target of this, and there are many more, but I'm only going to touch on these 3, is to ensure that at least 30% globally of land areas and sea areas are conserved through protected areas or other effective area-based conservation measures. And for this recommendation, really these stable, intact lands should become some of the major priorities for protection to promote climate resilience, because they not only have the stability and climate standpoint to let biodiversity persist in those under climate change, but they also have the ecological integrity to maintain biodiversity that's threatened to any kind of disturbance. So this is a really, really important one. And because we know that these stable, intact lands find themselves in a wide range of contexts, that protection is going to have to take on a range of different types, from strict nature reserves and very, very high wilderness areas that are not impeding with local communities, to multi-use areas, to areas that are protected and managed by indigenous communities. There's a lot of different recommendations that can come out of this that are relevant for natural resources management and local planning. And I'm just going to kind of run through them because they are highly redundant with some of the points I just make. And basically, to start off, incorporate life zone changes and stability metrics into even local planning. A lot of local projects that are funded to do small-scale restoration projects or to build a new nature reserve can utilize our information because it's at that very high resolution. Expanding protected area coverage and other effective area-based conservation measures, but specifically, again, targeting those intact landscapes at the local scale as well, can still be very, very helpful. Collaborate with and recognize the rights, knowledge, and practices of indigenous peoples. I've already touched on this a few times, but it's relevant in many, many different contexts, including at local scales. Maintain ecosystem integrity to help ease transitions to new life zones. Even in those areas that are projected to switch to a new life zone and support a different kind of potential ecosystem can benefit from having high ecosystem integrity, because we know that areas with high ecosystem integrity offer many, many adaptation benefits for communities, and oftentimes can help ease transition over truncated periods of rapid change. Establish corridors to accommodate species movements in areas projected to transition. We know that corridors are often used to connect blocks of intact habitat, and that's really, really important. But we understand now more than ever that those areas of habitat are potentially going to change, and we need to understand how to anticipate that and establish corridors effectively to weather that transition. And similarly, enhance the connectivity of ecologically viable climate refugia. We mapped these ecologically viable climate refugia at 1 kilometer scales, and often 1 kilometer is not enough for large terrestrial mammal species, even some birds and some reptiles. So we need to make sure that we're connecting small ecologically viable refugia to larger ones to build that network even more. Restore unstable modified areas with species assemblages characteristic of new life zones wherever possible. This I've already emphasized in some of the targets related to the CBD, and it's just worth reiterating here. And finally, continue to manage other threats such as fire, pests, and disease that can occur even in ecologically viable refugia. This point is really important because the model of life zones that I showed is only one sort of metric of instability, only one axis of risk. And there was a really cool new science paper that came out a couple months ago that looked at the same life zone metric from our paper as one metric alongside 2 other metrics of climate risks to show where they had similarities and differences, and found overall they were very poorly correlated, and they're different kinds of models. And this just goes to show that even though you might have a stable area in terms of a life zone, you still might have extreme temperature changes, still might have other threats ongoing that need to be managed. And so that's important to keep in the back of your mind. I just want to conclude the talk today by showing these cool visualizations that I did not create, but I loved to look at and think about all the time. The one on the left is a video showing long-term temperature changes from, I think it's 1850 out to 2100. And then the one on the right is global land cover change from 8,000 BP to negative 50 BP, just to remind us all the time that this is what's happening. We cannot view, as conservationists, the world as a static entity of this is what the climate is, this is what the land use is, this is what we're dealing with. We have to think about these transitions because this change over time is continuous, it's always happening, it's going to always happen, and this has cascading effects on what we find in the landscape. So I just put this up here because I feel like conservationists need to remind themselves of the dynamic nature of ecosystems, of distributions, of a constantly moving target for conservation. Is if we don't do that, we're really going to fall short in bolstering the resilience of these communities over the long term. So with that, I just want to thank you all very much for coming. Really encourage you to reach out to me if you want to talk later on. And want to thank all these individuals and support from our institutions to be able to fund and support all this work. Thank you very, very much.
Paul, thank you so much. We do have time for questions if anyone has a question for Paul. Alex.
Yes, so my question's about how you think about climatically stable refugia in the context of other strategies to adapt to climate change. You talked about at the beginning shifts in life zones and populations, and one strategy for that would be to try to keep pace with climate change and make refugia or make protected areas where there's not that biodiversity currently, but there will be. And then the refugia is kind of a strategy at the opposite end, and it seems like it has the advantage where you don't have to predict really precisely how quickly populations are going to move. But in the context of conservation decisions, you're always going to be making those decisions in the context of trade-offs between those two options. And so I'm curious if you see the focus on stable refugia as a strategy for operating under low information, or if there's some other advantage that, relative advantage that you see to taking that strategy.
Yeah, that's a really good question. I see the life zone model and the climate stability aspect of that as really informing one set of strategies. And one set of strategies is to protect what has been in a place, what is likely to continue to occur there, and have an understanding of the investments we've made in certain areas, understanding if those are sound investments or if we're going to have to think about doing things differently in those places we've already invested in. You can't just pick up a national park and move it somewhere else. Those are already kind of locked in. We've already invested so much into those. And the climate stable areas can also tell us about where, those investments are going to be, we're going to be managing in the same way versus what we're going to have to do alternatively. And the other aspect is that the life zone system kind of says something about the priorities for when we're trying to restore things and adapt through creating an ecosystem that is going to facilitate some kind of species movement or some kind of persistence of organisms. It has a lot of relevance for that into making sure that the actions that are taken there to do that restoration are not sort of invested in just to have to redo them a little while longer, just a way down the track because they're likely to transition to something else. So I don't know if that quite answers your question, but there's kind of multiple different applications that you can use this system for that fall across the restoration to protection sort of continuum.
In the back.
Yeah.
And especially in that there is almost no absence of natural or human appropriation of natural resources, and that's virtually non-existent in the world. So you could talk about intensity of natural resources, something like that. But my question was about the choice of setting a priority for conservation in areas that have low rate of natural resources. Because it seems that that places again an undue burden on global south countries and from your map also on some poor regions. But it seems that it extends sort of North America and Europe from any conservation duties. And I was just wondering, what you thought about maybe, sort of precisely targeting these sort of intensity regions that are stable from your model as conservation, like potential conservation.
Yeah, thank you. I really take your first point because we've struggled with that terminology a lot, and it is always a challenge to put it in the appropriate context. And there's a huge debate in the literature about when that context should even be. So that point's very well taken. The second point is I think I disagree a little bit. I think that there is a huge burden in northern countries and in the US, and the map might show there's very little areas of intact, but that means there's still a wide area of the United States that's in the stable category and modified, and there's a huge, I would say, conservation need to work in restoring a lot of those places. And this map kind of helps show where that restoration is possible in terms of achieving some kind of climate resilience. And in a lot of those areas, there are also areas that I think would benefit people as well, improving watersheds, and a lot of different natural resources that communities could take advantage of as well. In the global south, I think you raise an important issue, and projects like this often do have to be very careful about showing, yes, you're responsible for this. This is what you should be doing. Intact areas are here, so therefore, you need to do this. This is something coming from outside, telling you how to behave, how to act, and I'm very nervous to do that. I put up these kinds of maps to show a lot of times where others are already taking actions of some certain kind in the conservation world for carbon sequestration, to develop RED projects or other kinds of actions, and just to tell them, look, that already has had a huge impact on the people and the livelihoods in those areas, and it could actually even change even further because of these kinds of contexts. So I think there's some ways to utilize that information, not into a prescriptive, this is what you must do, but as a sort of, this is something that information that would be helpful to prepare for. And that's the kind of way that I'd like to kind of put it out there.
So thank you for the presentation. So a lot of the results that you produced are a function of the ability to basically categorize these life zones into different, each location to one of the life zones.
Yeah.
The ability to, and then you get the switches, which give you the information that you need. Presumably when you reproduced the Holdridge approach and generated the life zone map as a function of the climatic variables, you had a probabilistic assignment of location.
Yeah.
And so I guess when you did that, it must have been an area that must have been 50%, so on, so on. And I guess if you kind of treated it more continuously, do you erode some of the conclusiveness of what you produce? That's my question. That's a very generic question.
No, but that's a very, very important question. And we actually were starting to do that because we wanted a continuous metric. And it's hard with the life zone system because it's not a very continuous system. Right now, you're right. For any given pixel on Earth, you have the temperature and the precipitation that's then orienting you into that triangle sort of space, and then you pick the closest one to give you that assignment. And you could be right on the edge of a life zone and move a tiny bit into another one, and that is classified as a shift. And you could be in the dead center and move all the way to the edge, but stay in the same life zone and be and seem stable. And that to me is somewhat problematic. And so that's what you're getting at. If we could have some kind of a continuous measure of the life zone sort of space shift, we could attempt to look at that and see how those changed areas, how similar that is. It's a little bit of what has been done in the climate stability metrics, because even though the climate stability metrics that I showed in one of the slides uses a range of variables, they use a principal component analysis that pretty much just collapses it to temperature and precipitation anyway. And those models do show very different areas of stability versus change. The really big difference in those approaches, though, is that the principal component analysis, or that the continuous shift approach, operates in a linear fashion. Meaning, if you're at the very polar region and you shift a 1 degree temperature and you raise 100 millimeters of precipitation, you're experiencing the same amount of change as you would if you were in the tropical rainforest with 1 degree temperature and 1 millimeter in terms of that metric. But in reality, a 1 degree shift when you're already at 30 degrees is not a huge deal relative to your sort of baseline. And that's what the life zone model gets at, which I think is an advantage, and I think I failed to mention it, and does not lend itself well to that continuous those continuous measurements. So I'm grappling still with how to do that sort of computationally, but I'm very interested in that problem. And we have a working group that's convening in January at the University of Queensland to kind of discuss that as a potential next step. So I think it's an important issue.
Well, Paul, thank you so much for your presentation. Welcome back to Princeton.
Thank you very much.
We really appreciate it. And Paul will be up here for at least a few minutes
Yeah.
if there are additional questions. Paul, thank you very much.
Thank you.